the properties of vector product that I was talking about. So we've seen the entire procedure to find out the vector product of two vectors. Vector product is also known as cross product. So we've seen how if I give you two vectors, you can actually find what is the cross product of those two. We've seen that it results into a vector. We've seen what is the direction of that vector, what is its magnitude, right? But let's now look at a few properties of this vector product, just the way we saw the properties of scalar product, because some of these properties will directly be used without any sort of derivation when you solve problems and when you practice it over and over again, especially when it comes to physics again. A lot of vectors that you're studying in mathematics will be actually repeated, and physics will make sure that you're thorough with a lot of those things. So right, that's why it gets important to study vectors, because it's not just important from the maths point of view but also from the physics point of view. So let's look at the properties of these vector product now. The first property says A cross B is equals to minus B cross A. Now this is very different from dot product, because dot product was A dot B is equals to B dot A. Can you notice the difference? Yes, the difference is of the minus sign. Here this means that obviously you can say that okay, cross product is not commutative. So cross product is not commutative. In fact, the right term is it's anti-commutative because of the negative sign. What does this negative sign imply? Let's actually look into that now. So if I have a plane which has two vectors A and B, now first of all, A cross B. What is A cross B? A cross B is nothing but AB sine theta n cap, right? If the angle between them is theta, right? So if you've not followed what this is, then just look at the previous video, because that video talks about finding the cross product, the procedure for finding the cross product. So this is your B, this is your A, right? And this is your theta. So AB sine theta is the magnitude, n cap is the direction of this A cross B. Now what is the point is, what is the direction? Is it up or down? It's perpendicular, I know. It should be perpendicular to this green plane. The direction of this n cap and this vector indirectly overall should be perpendicular to this pink plane. Should it be up or down? For that what we do is we take the screw. So AB is like this, screw is like this. This is your A, this is your B. You rotate from A to B through the smaller angle, right? So you're rotating like this, that means the screw will go down, right? So this is downwards. Let's look at B cross A now. So B cross A will have similar terms. This will have a BA sine theta. There is no change here, but there will be a slight change here. Let it be P cap, right? The vector which is along B cross A, let that be P cap. So if I have to find the direction of P cap, first of all, P cap has to be perpendicular to this pink plane, because this is also a cross product between A and B. So this P cap also has to be perpendicular to this pink plane. Now the question is whether it's downwards or upwards. So for that what we will do is we will use the screw rule again. So let me use a different color. This is your A, this is your B. Now you need B cross A. So you will rotate from B to A through the, so this is your smaller angle. You will rotate from B to A now. So you will put a screw here, and now you will rotate from B to A. So you will rotate like this. That means your screw will rotate like this now. Initially it was rotating like this, now it's rotating like this. That means it will go up. So your P is in the upward direction. P cap is in the upward direction. So this is upward. Now I have a vector which is pointing downward, that's called n cap. I have another vector which is pointing upward, that's called P cap. What is the relation between P and N? P cap is equals to minus n cap, right? Because it's the negative of that vector. So I can replace this P with a minus sign. I can replace this P with a minus n cap. Now if you look at this and this, what is the only difference? The only difference between them is this negative sign. Everything else is the same. If I write B cross A, I can also write it as, instead of AB sine theta, I can write it as BA sine theta. It won't make a difference. I can write it as n cap, and I can take this negative sign here, and this quantity is nothing but my A cross B. So B cross A is equals to minus A cross B. So what you have to understand is, if I reverse the order of the cross product, I have to account that by putting a negative sign against the expression, right? So this is a vector, this will give rise to a vector, this will give rise to a vector. These two vectors are exactly opposite to each other. That is the whole point of this property. Let's move on to the next property now. So the next property goes like this, and that is A cross A is equal to 0. So these two are vectors, their result will also give rise to a vector. That vector is a 0 vector. That's the whole point. If you look at A dot A, that was mod A square, right? If you remember the properties of cross, dot product. Here A cross A will give rise to 0. Why is it giving rise to 0? Let's look at that. This is because A cross A is equals to A, or which is mod A bar, into A, which is mod A bar, into sine of the angle between A and A. What is the angle between A and A? It's 0, right? This is your A and this is your A. So angle between them is 0. So sine 0 is 0. A cross A has to be 0. Even if you have an n cap here, it doesn't matter because you're multiplying that to a 0. So everything will become a 0. So your next property is simply this. It is simply A cross A is equals to 0. So you never cross a vector with another vector with the same vector. You'll get a 0 as a result, right? It's not right to say never cross it. Sometimes you might just need to. The whole point is, if you cross a vector with itself, you'll get 0. You'll get 0 as a result. Just like your scalar product, your vector product is also associative. It's distributive. This is your distributive law. A cross B plus A cross C. So just the way A dot B plus C was A dot B plus A dot C, A cross B plus C is also distributive. So this is your distributive law. So remember that about your scalar and vector product, that both of them are distributive. So they follow that property. We are not proving this now. The only thing that you can remember for both this and this is that B is a vector, C is a vector, B plus C will be another vector. If you cross A with that vector, that's equivalent to crossing A and B, A and C, which will give rise to two vectors, and adding those vectors, the vector that you get is the same as this. So basically I'm just narrating the property that's there, but if you do this narration to yourself, you'll be able to remember it much better. So distributive law is valid for both your vector product and your scalar product, right? Coming to the next property, and the next property is this. Two non-zero vectors, A bar and B bar are collinear only if A cross B is equal to 0. Now this makes some sense. What is the reason? If I have two vectors A and B which are non-zero, then A cross B is AB sine theta n cap. Now when is the only possibility that your A cross B is 0? When can that happen? Because this A is not 0, because it's given they are non-zero, B is not 0, n cap anyways is a unit vector, so it's not 0. What should be 0? Sine theta. Only then your A cross B will be 0. Sine theta is 0 means your theta is 0 degree or 180 degree. That means your vector A bar and B bar are either along the same line, so your A bar is also like this and B bar is also like this, then the angle between them is 0, or they are opposite. Then the angle between this and this is 180, right? In both cases they are called collinear because they are along the same line. So collinear means the angle between them should be either 0 degree or 180 degree, right? So two vectors are collinear, or you can also say two vectors are parallel if and only if A cross B is equal to 0, provided both are non-zero vectors, because if any of them is 0, then the product will anyways, cross product or dot product, whatever it is, anyways everything will be 0 if one of the vectors is 0, right? And then you'll have no point in discussing about collinearity, because the vector itself is a 0 vector. Collinearity for a 0 vector is not defined because direction for a 0 vector is not defined, right? So with this, we complete this property. Let's move on to the next few important properties now. Let me make some space. Coming to the next property. Now this one is a very crucial one because you'll be using this again and again whenever you have to find the cross product of two vectors in their component form. This will be very useful. So this property, first of all, says I cross j is equals to k, j cross k is equals to I, k cross I is equals to j. So you guys already know what ijk is. You guys already know that I dot j will be 0, j dot k will be 0. So if instead of these crosses, if I replace these with dots, then everything here on this side will become 0. So this is something that you have already seen, right? So let me just show you how to memorize this order. You can put an I here, a j here, a k here, right? I cross j in this order should be k. J cross k in this order should be I. K cross I in this order should be j. I hope you remember the process. J cross I cross j should be k. J cross k should be I. And k cross I should be j. Right. So just remember this order is very important. Let's actually look at one of these and how, let's look at this first one, how to actually check what the order is. So basically, first of all, if you have to, prove this, you have to draw the coordinate system perfectly. So this is my x-axis, this is my y-axis, and this is my z-axis. This is what I've been doing. X-axis, y-axis, z-axis. Now, let's start putting it ahead. My I cap is a unit vector along this direction. J cap is a unit vector along this direction. What do I need? I need I cross j. So I is like this, j is like this. I need the direction of I cross j because first of all, what is I cross j? I cross j is mod I, mod j, sine of the angle between them, which is 90, into some n cap which is perpendicular to both I and j. So if I have a plane containing both I and j, so for example this is my plane, this is the plane containing both I and j. So your vector has to either come out of this plane or go into this plane. Any of these two can be your n cap. But I need the direction, so what I will do is I will put a screw here. I need to rotate from I to j through the smaller angle. Why am I rotating from I to j? Because it's I cross j and not j cross I, right? So I to j is a smaller angle. That means this is my rotation, right? So it's like you're putting a screw here and your screw is rotating like this. Imagine, put a screw on your screen right now in the same manner and imagine how it will move. It will come out, right? Your screw will come out. So that means this is the direction that you have to take. And what is this direction? This direction is your z-axis according to this. So that means, first of all, your new vector has a magnitude mod I, mod j, mod sine 90, mod n, which is all of them are 1. All of them are 1. So your vector has a magnitude 1 and it is along z-axis, right? What is that vector? That vector is k cap, right? So that is why the result is k cap. Similarly, you can verify it for the other two. But in the examination, you won't have the time to verify. You have to memorize this order. And how will you memorize this order? You will remember that using this circle. This circle will help you memorize this order in this manner, right? This was a very, very crucial property. Let's move on to the next property. Following next property, this property is also extremely crucial. In fact, even more than the previous one, because this is about finding out the cross product of two vectors when they are given in their component forms. So remember, most of the times you will see your vectors in component forms like this. B bar is equals to B1 I cap plus B2 J cap plus B3 K cap. These are two vectors in their component forms. The green vectors that I've been drawing until now, this A and B can be any of those, right? This A and B can be any of those. So instead of drawing them as arrows, I'm now showing you these vectors as component forms now. So fine, if you had arrows, then you were very happy, you had the angle between them, and to find A cross B, what you did was AB sine theta. This was the magnitude of your resultant vector. For the direction, if this is AB, you would put a screw, rotate from A to B, and this will go down. So n cap would point downwards, right? So this is the magnitude, and this would give you the direction, right? This is what you were doing. But what if I give you vectors in component forms? Now you don't know the angle between them directly unless you use some angle formula or something. You don't know how they look, how they are oriented in space, right? But still, if you have to find the cross product, first of all, let me test your memory. Let me actually test your memory. If you remember how to find out the dot product between the two. So if I ask you what is A dot B, what is going to be your answer? The answer is A1 B1 plus A2 B2 plus A3 B3. We have already seen the proof for this in the properties of dot product, that only the x components will multiply, and this x component when multiplied with this or dotted with this part, this when dotted with this part, it's all 0. Only this and this dot will be non-zero. Only the dot product of this and this will be non-zero. Only the dot product of this and this will be non-zero, and these three will ultimately add up to give my dot product. What if I have to find the cross product of these two? So this was dot product of the two vectors in component form. What is the cross product of two vectors in component form? For that, what we do is I take the vectors and I take a determinant. I take a 3x3 matrix basically, because these are vectors in 3 dimensions. Even if they are in 2 dimensions, this formula that I'm going to give you, or this method that I'm going to give you, is still valid, because if they are of 2 dimensions, for example, if this vector A bar is only in the xy plane, then at max what will happen is your A3 will be 0, right? Because if it's in the xy plane, only x components and y components will be non-zero. Z component will be 0 because the vector is only in the xy plane. So this will be 0. Likewise, any of these 3 can be 0, and depending on that, your vector will be oriented in space, right? So you're supposed to write, if you are starting from A and going to B, if this is A cross B, then because it's A first, you will write the components of A in the second row. You will write the components of B in the third row. You will write the components of B in the third row. Then what will you do in the first row? In the first row, you will just write I cap, J cap, K cap. And now you will take the determinant of this matrix. You will take the determinant of this 3x3 matrix. And if you guys already know how to take the determinant, you would know that the determinant of this matrix is nothing but this. A2 B3 minus A3 B2, basically cross multiplying these two. Then taking a minus sign, now cross multiplying this product of this and subtracting this product. That's A3 B1 minus A1 B3 J cap, plus taking this K cap and taking the cross product of this two in this manner. So basically A1 B2 minus A2 B1 K cap. Now if you don't know how to find the determinant of a 3x3 matrix, you're supposed to look at the determinants chapter for that, right? So when you come to vectors, you are already supposed to know how to find the determinant of a 3x3 matrix. So this is what the determinant is. So now you can look at this. A cross B is also a vector. This is a vector. So this must have x components, y components, z components. The x component is this, and then that is multiplied with I cap. The y component of this vector is this. This resultant vector A cross B is this. It's multiplied with J cap. The z component of the resultant A cross B vector is this, and it's multiplied with K cap. So it's very similar to this format, right? So these vectors are in the component form, this is in the component form. Even the resultant vector is automatically in the component form. So remember this matrix, don't mess up the order. What if I ask you B cross A? The question is, what if I ask you B cross A? What do? You simply write IJK first of all. In second row, you will put B first because B is first, right? You will put the B's components, B1, B2, B3. In the third row, you will put A's components, A1, A2, A3. And now you will take the determinant of this matrix, and that will give you the result. B cross A. With that, you can also actually verify this first property, B cross A is equals to minus A cross B. You can actually verify that if you take these two vectors in the component form, right? So with this, we complete this very, very important property. Remember this order, remember this method. I can't emphasize on how important this is, because you might get direct questions or indirect questions. I can't even specify the number of times you'll be using this when you study IIT, JEE, mathematics and physics. The number of times you'll be taking out the cross product using this manner. So you have to be extremely thorough with this right away. So with this, let's move on to the next property. Now let's look at the final property of vector product. This is a useful property because a lot of times, especially for 3D geometry, this property is useful from the 3D geometry perspective, because they might just end up asking a question which might involve, or which might involve this concept that I'm going to teach you here. It says, let's look at the statements one by one. The unit vector perpendicular to the plane of A and B is this weird thing. Is it actually that weird? The answer is no, because A cross B is AB sine theta n cap. Now we already know that this part of the cross product represents the magnitude of the cross product. That means this part actually represents the magnitude of A cross B, right? And that's multiplied to n cap. So I'm just dividing on both sides with mod A cross B. So A cross B by mod A cross B is n cap, right? That's all that this first part is saying. The unit vector, which is your n cap, which is perpendicular to the plane of A and B. Yes, n cap is perpendicular to the plane of A and B. I've been seeing that. And this is equal to this quantity, and that's what I've derived. And a vector of magnitude lambda perpendicular to the plane of A and B is this thing. So the same thing, but it is multiplied with a plus or minus lambda, right? What does this mean? So let's look at the whole process now, what's happening here. I have a plane. This plane contains what vectors? It contains A bar and B bar. Now this A and B, I need a unit vector which is perpendicular to both A and B. What is that unit vector? That is A cross B by mod of A cross B. That is my n cap. Is it pointing upwards or downwards? For that I'll put a screw and I will see. So what you have to do is, you have to put a screw here and you have to rotate from A to B through the smaller angle. This is a smaller angle, so rotate from A to B. It's going downwards, right? That means my n cap that I was looking at was downwards. This is the n cap that I'm representing right now, right? This is perpendicular to the plane containing A and B, right? So this is perpendicular to this plane, this n cap. Now I need a vector of magnitude lambda which is perpendicular to the plane of A and B. So this has a magnitude 1. If I want to make its magnitude lambda, I will just multiply this with lambda, right? Then I'll get an extended vector of magnitude lambda, because if I want the magnitude of lambda n, then that is mod lambda into mod n cap, right? And this is basically lambda, and this mod n cap is 1. So I'll have the magnitude lambda, right? So I'll get an extended vector, I'll get a new vector whose magnitude will be lambda. What if I multiply this n cap with minus lambda? Then I will get the same vector in the upward direction. This is my minus lambda n cap, because my n cap is downward, lambda n cap is also downward, and minus lambda n cap is upwards, right? But in both cases, even this upward thing, even this upward arrow is perpendicular to the plane, right? So even this is perpendicular to the plane, and even this has a magnitude lambda. So that's why both your plus and minus is valid. So ultimately the whole point of this property was, if you have two vectors and you need a third vector which is perpendicular to both these two vectors with a specific magnitude, you're supposed to multiply these two vectors, you're supposed to take their cross product, you're supposed to divide this with the magnitude of the cross product. This will give you a unit vector which is perpendicular to the plane. Now you can multiply this with plus or minus lambda. So this will give you a vector of magnitude lambda either in the upward direction or in the downward direction. Now whether you want it in the upward direction, if you want it specifically in the upward direction, then you can take minus lambda in this case, because your A and B are like this, right? Because your A and B are like this part which represents your n cap is downward, and if you need an upward vector, then you will take a minus lambda. But if you want a downward vector, of magnitude lambda, you will take a plus lambda into this. And if your direction is not specified, whether it's upward or downward, only what's specified is, okay, it has to be of magnitude lambda and it has to be perpendicular to A and B, then you can take both plus or minus. You will get two vectors, right? So this was the final property, which was slightly important and slightly interesting, because in some problems themselves start with this concept where they'll give you two vectors and they might just ask you to find the third vector, and the rest of the problem will actually start from that point. So then when such questions or such situations come, you must think of this property, right? So with this we complete the properties of vector product. Let's look at the next part of the chapter, which is basically physical interpretation of cross product. So we'll also look at geometrical interpretations and physical interpretations of cross product. Let's proceed.